All right, let's get started. Today we are going to kind of bridge a couple of topics. We've kind of taken our time talking about hazards and how to prevent against them. It's good. You're not going to get as much experience this semester in building that in the lab as a more typical 381 semester would. So that's fine that we're covering them in a little bit more detail and you're getting that feel for what they're doing, answering some homework questions about them, but not really building it yourself by and large this semester. Saw a lot of activity last night, as is custom. People working into the late hours and being very tired, and I understand that. Um, a couple things, I do want and require everyone to submit their project B on time. I think there's pretty much a fairness issue at this point with the amount of weeks we had for project B. Submit what you have by the deadline, and let's move on to project part C this week. Demos can still happen after the fact because the TAs only have a limited time budget to schedule those demos. But for the remainder of that, the report and all that, get that submitted by the deadline, and for fairness, so that we can finish up the semester in the next 3 weeks here. Um, Secondly, and maybe as a separate issue, I think you should take a moment and breathe a little bit once you've hit submit on project part B. And even if it's not perfectly working, and I know a lot of people still have little bugs here and there. Some of you still have big bugs, but a lot of you just have little bugs here or there that you'd really like to finish up, but you're running out of time or have run out of time. And I understand that and how that can be a little disappointing that you put so much effort in and still the end result isn't exactly right. But you should look back and realize, where you've come in terms of what you've been able to do, right? We started this semester, playing with logic gates again, kind of like your 281 semester, but we were starting with just very basic components. And we have scaffolded that design to a processor implementation that is very close to being something that you could run real world code on. It's not 100% of the way there. It's like 95% of the way there. And that's pretty impressive, right? I mean, that's something that, in past would take, teams of 30 working all hours of the night as their full-time job to be able to build such a thing. And you've been able to bootstrap it. You've been able to get that working from a gate to a register file, adding an ALU, adding a memory, adding all the control logic for it. And I think you should, pat yourself on the back, even if it's not perfect. There's always bugs anyway, right? You can look at what Intel releases for their processor documentation, and there's 300 pages of processor documentation, and then 300 pages of basically errata or bugs. Here are all the things that are wrong in our processor that we would like to fix one day, and we'll get to it when we get to it. And so yours has some of that balance as well, I think. But at the same time, I think that's incredibly impressive that you went from knowing not a single thing by and large about hardware design at this level and about VHDL and using tools and a platform that are not ideal, that have their own foibles that make life a little bit complicated for you, unnecessarily so sometimes. And you've built a working processor that takes code that GCC can compile and can run it. Not super fast, not with all the greatest bells and whistles, but it can run that code. And think about that. Think about that once you've hit submit and you breathe for a minute and then move on to the pipeline processor, because that's extremely impressive. And that's something a little unique about Iowa State University's program and what we do in the computer engineering courses that we have. That we don't just have you work on a Java simulator. There already is a good Java simulator. We're building an actual hardware that we can map to an FPGA based platform. So be proud of what you've done, even if it's not 100%, even if it's 50%. You've done a lot, and it's I'm really impressed with what you've been able to do. So in terms of where we left off on, I don't even know what day it is at this point. Where we left off on Monday, I've been burning the candle at both ends these last couple of weeks in terms of development work, research work, and helping support this class. We were talking about the performance implications of our control hazards. And we looked at a couple of approaches that we could take. In fact, I'll go back one slide here. Where we left off was that one such approach that has promise, um, although there's a lot of little details the textbook diagrams don't cover, you're now familiar with that, I think, is that by moving the branch logic as early as possible, that's what this little equal sign here is corresponding to in the figure. By moving that as early as possible, our penalty, our pain associated with a branch is just that one cycle, which is the same as with a jump. So normally we would say jumps we can figure out in one cycle and branches take a few. And now we can say, well, both branches and jumps we can sort out by the end of that ID stage of our processor, which is still not ideal in the sense of It's not the same as a forwarding solution that we have for data hazards. Forwarding is very tricky because of how early we need to update the program counter for our control hazards here. But our overall impact, if this was our primary solution and our final solution for control hazards, is that, well, given that these branch instructions aren't that common, some 10% or so, in this case, the example is 15%, we're adding that extra amount to our overall CPI. So it's not great. We did all this work to build this nice CPI equals one pipeline. And then we're seeing that for some load use cases, if we're not careful, as well as now for all these branches and jumps, we can't quite reach that ideal. Another solution, and there's some confusion that is actually due to this in terms of both looking at old documentation for MIPS, looking at what the textbook says in some places because they're inconsistent in places. But just like we had this idea of a load use slot, which is the instruction immediately following a load instruction, if we can fill that with something useful that doesn't have a data dependency, we're in good shape, right? We don't have that hazard, that load use hazard anymore. And compilers are still very free to do that. Again, we define a variable and we write to it because we expect to have to use it very soon afterwards, but not necessarily immediately afterwards, not necessarily the next instruction afterwards. If we can find something else useful to put in there, let's put it in there. And so early MIPS processor implementations required that either you put something useful there or you insert a no-op there. And similarly, early MIPS processor implementations and some references you'll find if you just Google for these terms online, we'll mention this as well, have a very similar concept for our branches and jumps, referred to as a delayed branch. Or also the same concept is a branch delay slot of one. Meaning that the assumption then, and this is an assumption that the compiler then would have to take into account, is that even though logically we have a branch instruction, which means we either continue on, this is my hand showing continue on, we either continue on or we go somewhere else, the implementation assumed that because of this exact issue, because of this pipeline and this control hazard issue, um, you're gonna always execute the next instruction anyway. That's what's referred to as a branch delay slot or a branch delay of one, meaning that the branch is still our valid instruction that we care about, that there's this label we're going to eventually, but the early MIPS processor implementation said, well, because of this exact issue in which we're paying this penalty of one cycle basically for every branch or jump, let us, instead of stalling the pipe processor and implementing any of this control hazard logic whatsoever, let's just always execute what the next instruction is anyway. And again, similar to the load use slot where you have to put something meaningful in there for this to be, something correct has to be moved in there. You can't break dependencies for this to work. That next instruction after the branch instruction would also have to be filled by the compiler or you guys as the assembler um, with something that it's okay to have executed. It is correct to have executed. And it kind of leads to this interesting situation where things are almost sort of out of order in our execution, but not really. We're having the compiler tell us that, yes, even though this is a branch, and as we logically trace the code, we go to L next if the branch is taken. In this case, if we assume that there is a branch delay slot in our MIPS implementation, we're always executing whatever that next instruction is. And of course, just like in the load use example, if we can't find anything useful to put after the branch instruction, because there's just a lot of data dependencies and there's just nothing useful that we can put after the branch that we were okay with always having be executed, then we put a no op there. And that was the early MIPS solution, was to have both load use slots, to have branch delay slots. That's where I got a little tongue twisted on Monday where I said, does the MIPS processor have interlocked pipeline stages? The answer is yes, right? We are implementing the interlocks. We're implementing the delay, the forwarding and the stalling and the flushing and all that. That's our interlocks, hardware interlocks. But the initial implementations, one of the value propositions of MIPS is don't have any of that. Keep your processor as simple as possible, and then let software take care of some of those challenges. And historically, there has been a lot of give and take with regards to what extent should architects rely on the compiler folks to generate code that works really well on our architecture, or so to what extent should compiler folks rely on an architecture to effectively and efficiently implement the instructions that they emit. And if you look at the history of computer architecture, it's been waxing and waning over time in terms of how much we have to rely on a very clever compiler which the original MIPS would count as that. And how much do we realize? Well, that's actually a very hard problem to solve in general. Let's have our architecture be a little bit more resilient to different instruction mixes and getting better performance out of different instruction mixes. Today, it's the reality of computer architecture is it's still very much a hybrid. Um, for most of the latest and greatest, instruction set extensions that get released, it takes several years for compiler writers to really catch up. There are some exceptions to that. If it's a company that has complete control over both the software infrastructure and the underlying hardware, then usually those two things are co-designed and co-developed. But otherwise, new ISA extension comes, 512-bit AVX instructions, and it takes a very long time for a compiler to actually be able to emit those instructions. If you want to use those instructions, you have to hand code them assembly in your code at least to start with, and that's also a bit of a pain. But that is why, going back to this branch delay slot, that is why you'll see some documentation in a couple places in the textbook, as well as online when you look, that suggests that the value that's getting encoded for jump and link, for example, that's where it really comes into play, would be PC plus 8 and not PC plus 4. Because that is assuming there is a valid branch delay slot here after the jump and link instruction. And when we return from the jump and link with our jump register, we don't want to execute this instruction again because that assumption is that we've already executed it. And in Mars, there is a button we could click saying include branch delay slot or something, I think is what the little checkbox is. We could have had that implemented by default, but by default it is off and we keep it off. And so we do not do this, and so we should be jumping and linking to PC plus 4. If you insert a no op, doesn't matter, right? Technically you're wrong and technically you're off by one cycle, but it's a no op cycle, so the tool flow doesn't even catch that that's the case. But if there is something, a valid instruction after the jump and link, then we do have to be very careful. Are we linking PC plus 4 or PC plus 8? Some debate about that. What is the correct approach? And my philosophy, and I think people have really caught on to that, is, well, what should this instruction do? I don't know. Check Mars. Mars is our standard that we're comparing against. Don't overthink that, right? The ISA spec can say something very specific. The textbook can have a throwaway paragraph that says something else. You Google online, you'll find even a third opinion. I have my own opinion that has been proven wrong on one instance this semester. Doesn't really matter. Ultimately, you're comparing against what the Mars output is for this. And that's why it's very good when doing any development to have a golden model to compare against. Mars is that for us. I'm not saying Mars is golden and it's perfect, but it's at least consistent and with something we can compare our implementation against. So just like I mentioned, early MIPS not having hardware interlocks for the load use hazard, that was also the case for early branch and control hazards as well. That instead of trying to do um, any of the stuff we're going to talk about with regards to flushing the pipeline, stalling that instruction, instead it was just put something useful there if you can. Otherwise, put a no op there and just acknowledge that your code looks kind of weird because it has an instruction that always executes, even though as we logically trace through the code, it looks like it shouldn't. There's a third approach, which is very commonly in use. In a sense, we're doing a little bit of that already, but not referred to as such. And the third method is referred to as branch prediction. So the third approach is to use prediction to handle branches. So determine whether or not a branch will or will not be happening based on some knowledge you can have very early in the pipeline, and then change the processor state accordingly here. So in this case, we've already moved this decision art hardware as early as possible. Arguably by default, we are assuming, and we kind of mentioned this on Monday, we are kind of assuming the branch is not taken, right, in our default implementation, because we execute PC and then, or we fetch PC and then we fetch PC plus 4. That's assuming the branch has not been taken. That is a type of prediction that we can do here. But as our pipeline gets more complicated, for more complex processors with deeper pipelines, the importance of branch prediction becomes a little bit more important. And so we can differentiate between that kind of static scheme, which is just make an assumption and correct it if wrong, to this more dynamic branch prediction scheme, which if you have a deeper, more complex pipeline, this does become more important. It requires a couple of things. It requires a separate memory storage to keep track of the last time I was at this program counter, what happened? Again, for an instruction for a program's execution, your branches are going to be where your branches are. They're not dynamically changing, right? You don't know what they are necessarily until you get there the first time. But after you've executed that branch the first time, in theory, we can store that state information somewhere. I ran into this branch instruction the last time I was at PC of this value. It's going to be a branch again. Let me use some knowledge about that branch instruction to make a slightly more intelligent prediction about what the pipeline should be doing next. So, not really laying out all the details of what that would look like from an implementation perspective, but some of these are very common features. The first is that branch history table or the branch prediction buffer. It's a buffer, so don't overthink what a buffer is, just a memory that you could look up to and grab values. So, in parallel in our pipeline, let me just go to a pipeline picture here to show what would be happening. And I know this has a lot more detail than what you maybe need to look at to understand this concept. In parallel, when we're using our PC to fetch our instruction from memory, we're also going to use our PC via some mechanism to look up whether or not that PC corresponded to a branch instruction or not in the past. We could talk a lot about how one would implement that. It's not that straightforward, right? The PC is this 32-bit value. In theory, we need a 2 to the 32-bit array of bytes in memory to hold our instruction memory. In practice, it's not so large. Same can be applied towards our branch prediction buffer. It'd be a smaller buffer. We may apply a hash function to get a probabilistic likelihood that we have a match here. We may just take a subset of the bits, which is a type of hash function as well, to determine whether or not the last time this PC came up, we have some confidence that it was a branch or not. But either way, that's the first start of the approach. First time that branch gets fetched, we would have no idea that it was a branch. It's just 32 bits coming out of memory. By the time we get to this decode stage for that program counter and that instruction value, we can now know, oh, it actually is a branch. And likewise, because of this manipulation of stuff into the second cycle of our implementation into the ID stage, we also will know it was a branch and it was a branch that was taken or not. And then that information, while we're updating the PC and doing the flushing and the stalling and all that stuff, because we incorrectly loaded PC plus 4, we can also update this secondary buffer here to say, last time PC value of 1 million came through, it was a branch, and some other information can help us. It was a branch, and it was a branch that was taken. Why do we think it's important? This is not a rhetorical question. Do your best with it, though. Why do we think it's important to know whether or not that branch was taken to be able to make better predictions about the next time that branch happens? Just thinking about code that we write. So again, conceptually, we have this buffer that keeps track of, it can actually keep track of two things. It can keep track of, was the instruction at this PC a branch? It can also keep track of, what the next PC was, so what the actual branch target was. It's a memory, you store whatever you want in there. And then it also would keep some information, the outcome at least of taken or not taken. Why would that be good to know? Oh, good answer. Oh, both of you, a lot of good answers. I didn't see that you were already posting answers here. That's absolutely correct. Now, we can't say for certain, obviously. We can't say, yes, we are guaranteed that if we took a branch, we're going to take that same branch again. You could write code that has all sorts of bad probabilistic branch behavior. But if we think about the code that we are likely to write, that compilers are likely to generate, why do we have branches in the first place, right? We have branches for our for loops. For I equals 0, I less than n, I plus plus. That branch is checking if I is less than n. And presumably, for n of 1,000, 999 times straight in a row, we'll have taken that branch. And that's not a synthetic example. That's a very realistic example of what would happen. We don't know exactly how many branches are taken or not taken in a given code. You could write that same for loop where the branch is not taken every single time and then finally taken at the end, right? You can always reorder equal versus not equal in your branch code. But still, the common repetition is something that's just always going to be the case in code that we generate. So because of that, we can actually use that to assume something about the future. This branch was taken. And in this simple branch predictor we're going to talk about in the textbook talks about it was taken, let's assume it'll get taken again. We could be more clever than that. We could say, well, it's been taken 3 times. Fool me once, shame on you. Fool me twice, shame on me. Et cetera, et cetera. Fool me 4 times, I should probably take the branch. That's what we could use to assume that, right? Hey, this branch has been taken every time we get there. Instead of waiting a whole cycle, instead of processing whether or not that branch should be taken or not, let's just assume now. It's been taken 99 straight times. We're on the 100th iteration. We should probably just take that branch. Right? So conceptually, that's what this approach is doing. As we're fetching the instruction memory, also fetch whether it was a branch or not previously, and fetch some knowledge about whether it was a branch taken or not. If it was a branch not taken, well, then just continue, right? And if we're wrong, we're wrong. But if we're right, we're no worse off than what we were. Same with if it was a branch taken. Now in our PC plus 4 logic, we can make that decision in multiple different places. We can now make it as early as possible to not even do PC equals PC plus 4, but instead to do PC equals last time this instruction executed what the next PC was for that branch prediction that we're making here. And modern deep pipeline processors care a lot about how to do branch prediction properly. For us, it's hard to get too worked up about it. We're talking about this 1 cycle penalty we're trying to save, right? So it's either correct and there's 0 cycle penalty, or it's incorrect and there's a 1 cycle penalty. So hard to care that. I mean, 1 cycle is still a lot as we did the math on CPI. It's hard to get too worked up about a 1 cycle penalty. If our penalty for a branch is 25 cycles, which can very easily become the case, we want to do as much as possible to prevent that from happening. And this is one such approach. There's no sort of golden algorithm for how to actually predict whether a branch is taken or not. And actually what modern processors tend to do is they tend to not actually overthink it. Team A has an idea for what would make a good branch prediction algorithm. Team B has a completely separate idea for what would make a good branch prediction algorithm. Folks in academia are publishing papers suggesting a third approach, number C. And modern processors tend to just try all three. Try all three and see which one does best over time. That's referred to as a tournament predictor. And it's not very scientific in a sense, right? It's, well, we don't know which branch predictor is going to work best. We're going to try all of our options and just go with the one that's been working best so far for this particular piece of code. But that is how modern microprocessors do it. The textbook branch predictor is presented here. The idea being that we could start with just a 1-bit predictor, which is if taken, take again, or if not taken, don't take again. And that's okay for certain scenarios. It does pretty bad if you have a nested loop with an inner loop and an outer loop, in which you would mispredict the last iteration of the inner loop, and then you'd be wrong again for that next time through the outer loop. To me, this is a pretty subtle, and the actual performance benefits of a 2-bit branch predictor versus a 1-bit branch predictor makes a nice homework question, but it's really hard to say in practice how much better this would perform. But the idea being you store a little bit more than just that taken, not taken state, and consequently, when you do that, you can have a little bit more resiliency towards things like nested loops in which there's a certain pattern to taken, not taken. So this is the 2-bit predictor, where because it's a 2-bit predictor, you can think of it as a state machine with 4 different states associated with it. And the idea is you can predict if something's taken, and if it is taken, you continue to predict that same branch is taken. Again, this predictor is per branch. If we have a completely different branch in our code, we have a completely different 2-bit representation for that other branch. If it's not taken once, you could think of this as really confident the branch is going to get taken. If we find out that it's not taken once for that inner loop, for example, now we're in the somewhat leans taken as opposed to heavy taken, prediction for our branch predictor here. We have some confidence maybe it's going to continue to be taken. It was taken 999 times in a row. Just because we didn't take it once doesn't mean we should give up on our prediction potentially. And now we're in this state where we really don't know. Only when there's 2 successive either not takens or takens do we move out of that state into the more confident state. And again, that's specifically for the scenario, and we have double nested loops. The nice thing, I guess, Nicholas, about the triple nested loop, you're right. The nice thing about a triply nested loop is you still have the same situation with the inner nested loop. So it's kind of the same situation, right? It's all relative to the higher order loop. So it still kind of works for that, but it is very much just kind of an academic exercise of you can show that for a nested loop, this 2-bit predictor would perform better than a 1-bit predictor. I won't belabor the point. There will be a homework question where you kind of roll through it and just show how you transition from state to state for a for loop and see that that's actually the case. Definitely nothing wrong with triple nested loops. Once you start to get to 4, 5, and 6, you have to start wondering about your code and saying, what's going on here that I have so many deeply nested loops? Am I overthinking? Am I underthinking the problem? Am I trying to be too clever? Am I trying to over optimize? Um, yeah, but still, you see it a lot in real code. Um, and I already mentioned this point. So even if you correctly predict whether or not a branch should be taken, or not. For that to be useful, you actually have to store the branch target offset as well. And that can all be stored in a single data structure. Program counter looks up was a branch, my prediction about the branch, or my state information about the branch, and where we should branch to, or not for that particular branch. You can kind of think of it as a parallel memory lookup with our instruction memory, where based on the program counter, we know both what the current instruction is, and we also now have looking up basically and calculating a prediction of what the next instruction should be. Again, that is a lot of work to remove one cycle, a probabilistic percentage of the time. If it's preventing a 25 cycle stall, that could be a very worthwhile thing to do. Any questions about that? We're about to transition a little bit here. Take a moment and breathe. Okay. Yes, so I saw someone was asking about the quiz today. Alas, no quiz today. Not on Friday as well. I'll push it to next Wednesday, our quiz. So I don't think people are terribly upset about that. But if you had planned on sleeping in and only woke up for the quiz, well, stay with us. You're here now. You might as well continue. But there will be no quiz today. This is just me talking today, apparently. Um, I think the remainder of this topic we've already covered just in different orders. So, talking about the difference between, and this is the first part of Project Part C, the difference between a bubble and a flush of an instruction. They are similar things. Dead week is not a thing this year, by the way, if you're asking that, this semester. I don't think I'm doing anything that would have been violation of even the old school dead week policy. The policy has always been if something is on your syllabus, especially on day one of the semester, you're allowed to have things during that week. It's not a complete quiet week. It's certainly allowed to have homework due during that week. Um, but there's two different types of things we're doing with our pipeline depending on our hazard detection. And they're similar, but you're not going to be able to implement them the same way because there are two different things going on. The first is we have to potentially stall an instruction. And installing an instruction, we're just telling it not to advance for a cycle. But in the process of doing so, we're inserting a bubble into the pipeline because something still has to get written to those registers so we don't accidentally repeat the instruction. So we basically are inserting a no op or inserting just the control signals corresponding to not writing any values in our pipeline. That's inserting a stall or inserting a bubble into our pipeline. That's one thing that we have to be able to do when we detect these scenarios. Certainly the load use hazard example. Separately, although it's very similar sounding, we also have to be able to flush a pipeline. That is an instruction that has to go away. If we execute that instruction, our code is wrong. Whereas when we delay or stall the pipeline, we just have to execute that instruction one cycle later. When we're flushing the instruction, that's because a branch is wrong. We should not be executing that instruction at all. It looks kind of similar, right? By stalling an instruction, you're basically flushing the current state of that instruction and letting that bubble proceed through. When you're just flushing an instruction, though, you're telling it that anything corresponding to that program counter should not be executed. Technically, it can make its way all the way through the pipeline, but you should really convert it to a no-op right away so you don't accidentally trigger data forwarding logic or other logic. You certainly want to make sure it doesn't write to the register file or to our data memory when that's the case. So building and modifying your pipeline registers for Project Part C will take you some days because an n-bit register is something you already know how to do with a write enable and a reset. But being able to support these two operations does require a little bit more thought. And I do want the teams, I do want you to think about that as you're building on Project Part C in the lab. And finally, as we're finishing up, finally, our pipelining topic here, there's a lot of different ways to do laundry. And consequently, a lot of different ways to do our pipelining here. We were doing in order scalar pipeline, is what I've referred to what we have been building. So for our in order scalar laundry, meaning in order, meaning we never switch the order of execution in decode stage or execution in mem stage. And scalar, meaning we only have one of these stages. We only have one primary ALU for which we're using the execute instructions. It's still vectorized in the sense we're executing a lot of instructions, but it's scaled in the sense that there's just one primary pipeline here. Well, to go all the way back to our laundry analogy, there are many pipelines that support out of order execution, where because of some dependency, and a data dependency is a common reason for this, it could also be a control dependency or control hazard. We allow other instructions to continue forward in the pipeline and just make sure we don't break any data dependency in our code. So it allows for dynamic execution of laundry in different orders. It's a little hard to imagine what that dependency, would look like in a laundry analysis. Why is there a dependency on one thing and not the other? But for our instructions, we already could see it that's the case. We have data dependencies between instructions. In an out of order execution processor, we allow those dependent instructions to wait while we allow other instructions to continue. That requires a lot more hardware to keep track of where each instruction is in the pipeline. In our current implementation, it was just those 5-bit register values is all we had to keep track of, right? To keep our data dependencies in line. For a 5-stage pipeline, it probably doesn't seem worth the effort. What is the actual gain going to be there? But if you have a 45-stage pipeline, then being able to allow other instructions to continue while the current one has to wait can be a very valuable optimization. Modern deep pipelines are all supporting out of order execution. But again, we talk about how things change in terms of what's the right way to build a processor over time. Um, Modern GPU architectures don't do any out of order execution whatsoever from a pipelines perspective. So it really depends. But if you look at a modern x86 Intel AMD processor, all their pipelines support some nature of out of order execution. That's about all we'll say about that, other than there's a whole other class where you get a chance to learn a little bit more about that. And then finally, our pipeline is a scalar pipeline in that we just have one of everything. A super scalar pipeline is one in which you have parallel resources, and that gives you that much more control potentially about how you're scheduling instructions. The laundry analogy is that you have a different set of resources depending on the type of clothing you're washing. It would be very similar to that, other than you just for a pipeline you'd have a different amount of resources depending on how many instructions of a certain type you want to be able to execute at the same time. Another way to think about that is if we just allowed there to be a couple of more ports on our register file and allowed it for us to have just a second copy of our ALU, we would basically be able to support executing two instructions at the same time. That's basically all that we're missing in order to be able to do that. And modern processors tend to support not an exceptional amount of superscalar execution of this type, but 4-way, 8-way, sometimes 16-way, where with these deep pipelines and with the potential to reorder instructions that are in these deep pipelines, we also want the option to fill as many different types of instructions in our pipeline at a time to allow us to keep those pipelines full. CPRE 581, which is a graduate level course, but if you've done well in this course, you'll be perfectly ready for that course, is where you would learn about out of order and superscalar execution. And finally, let's just circle back to what a real pipeline looks like logically. This is a Core i7, which doesn't mean anything anymore. This is a first generation Core i7 pipeline, so the term meant something back then. Nehalem architecture, microarchitecture from Intel, showing what a real quote unquote real pipeline can look like. MIPS is a real pipeline as well. ARM is a very MIPS-like looking pipeline, but this is what a more complex Intel-like pipeline tends to look like. There's some stuff we don't know yet, and that's what we're going to be getting to. All this stuff about how we're doing instruction fetch, we have this basically as PC connected to instruction memory, right? And that is still conceptually what's happening in modern processors. It's a lot uglier than that. So we'll be talking about some of that ugliness in modern, certainly more complex instruction sets. Our decoding is a lot more ugly than what um, you're able to do with your spreadsheet. I saw some pretty ugly spreadsheets though, to be honest. So ugliness is relative, but there's a lot more things we have to potentially decode depending on the ISA and depending on the edge cases in the ISA. Logically, though, instruction fetch to instruction decode. Execution stage is where you tend to see modern processors look a lot different than our 381 textbook version of the execution stage. Here you're seeing a couple of different things. Again, ALU slash shifter, that should sound kind of familiar. There's a couple of those. There's logic for doing the loads and store calculations. And then depending on the type of operation, there's all these custom units to support those custom operations that are extensions to the vanilla ISA that's already supported by the processor. But otherwise, this looks a lot like register read and our execution stage happening here. The difference is it is a superscalar, so there's multiple parallel pipelines basically that are being fed here and being executed, and then there's a lot of logic to keep track of instructions that are potentially executing out of order. That's our reorder buffer. We fill it up with as many potential valid instructions as possible, and we allow it to figure out which ones it can launch, which ones it can finish, which ones it has to hang on to. That is a big chunk of what we don't really know yet at the end of this class in terms of the complexity associated with that. And then finally, the memory stage looks a lot different as well, but conceptually, it's still doing the same thing. That's our load store logic here. We're starting to see all this detail about both TLBs, which we won't talk at all about this semester, and caches, which we will talk about starting in about 2 minutes here. Logically, it's still the same thing. It's generate an address, which is happening in our load store address calculation logic, and then connecting that using our ALU type logic to generate an address, and then connecting that to our data memory. It just so happens that in more real processors, where we have to support potentially a very large amount of memory, we can't just implement it as a single, SRAM lookup, a single cycle lookup. It tends to be a lot more complicated than that. That's ultimately most of what's happening in terms of this here. This is actually underselling it a little bit in terms of um, actual real estate on our chip. Potentially, even a majority of our total real estate is being spent right here. And all this time we're spending on our pipeline, it's still very important. It's still very performance critical. Is maybe 50% or less of our total transistor count for our resulting circuit for our pipeline processor. So it looks different. It's not MIPS. But my thought is you have the skills now, or we're very close to having the skills now to look at a diagram like this for whatever the most recent processor that gets released tomorrow is going to be, or the microarchitecture that gets announced. And to the extent that companies still provide this level of detail, they do eventually. Um, you should be able to understand basically what it's attempting to do. No one really has the skills to look at a picture like this and say, well, performance is going to be 10% faster. AMD, Intel have very large teams specifically dedicated to performance projection. That's building early simulators, doing microarchitectural simulation, and trying to figure out for the workloads they care about that they think we potentially care about, what is the performance going to be if they make these particular design decisions. That happens 5 to 6 years before the processor is even released. So we can't say anything specifically knowing performance. We have to look at benchmarks ultimately like everybody else. We should be able to understand the benchmarks a lot better, but we should be able to basically understand what these modern real world processors are attempting to do. They're always fetching, decoding, executing, and writing back the results to memory or back to the registers. The difference is just how many parallel pipelines there are, what kind of execution units they support, and there is some difference between processors with regards to that, and how they lay out their memory optimization strategy, which tends to look pretty similar from one processor to the next. There's a limited transistor budget. It's fairly large. It's in the tens of billions of transistors now for the most highest end processors. But all computer architecture is really trying to determine, how do I best allocate that budget? Do I have more cache? Do I instead decide that one more pipeline here is going to be really worthwhile? Do I add additional complexity here or here because that leads to fewer hazards at runtime? Those are the type of decisions that someone who would have the title of computer architect is trying to make. And they have to make those decisions well in advance before anyone touches a line of Verilog or VHDL. They have to project that out to see, is this, tens to hundreds of millions of dollars investment worthwhile or not? That's a performance projection. Having all said all that, as you look at the latest and greatest, and this is quite old now, even though it's a Core i7 line, you should be able to understand what they're attempting to do. You have that. If you didn't have that skill set before, I think you certainly have that now. Finally, here, and there's a homework question that I think was flummoxing people a little bit here. The phrasing of these questions is pretty important, and I'm taking them. I've always been taking the homework questions straight from the textbook. If there's an issue with the phrasing, with any homework, don't assume that we have it exactly right. It's always fine to ask for questions about what's happening with these homework questions. So this we have to make certain assumptions about what's happening in our pipeline to be able to answer this type of question, which is tracing code, not on a single cycle processor anymore, but on our pipeline processor with some sort of assumptions about what type of interlocks there are, what we're doing for data hazards, what we're doing for control hazards. Can we do better or can we make it worse? That's what the one homework question is asking here. This is straight from chapter 4 of the textbook with regards to this code here and what we're attempting to do to make this code potentially run faster. I don't expect you to become, deep experts in this, certainly if you're not going to be doing it in the lab this semester. But as we did talk about when talking about data dependencies, spotting them is relatively easy. Anytime you see the same register twice, you know there's a data dependency. We know how to spot the ones that we can solve via forwarding, or at least you can look back on the notes here and see, okay, I can resolve this and that and the other via forwarding. And then we also will know, if you don't yet, that those load use hazards are the one that get us. And there is one here, right? Load into T0 and then immediately use T0 one cycle later. So when this question is starting off by asking, can we make this code run faster? That's the kind of thing it's looking for. Are there things that are going to cause this processor to stall? And can we do something about it? So what can we do for this example? So I'm telling you, and I think this is correct, that there's a one cycle stall associated with that load use case. What can we do for this? Don't all jump out at once. Absolutely. Add IU. Right, so we have to look at the dependencies. Thank you. I appreciate you. And you see a lot of T0s there, which should make us a little nervous, right, about reordering any of those instructions because this is a write operation, this is a read operation, this is also a write operation, and it's tricky, right? As we talk about, this is a read operation for our store word instruction because we're writing to memory. We have to be a little careful, so we can do it. See if I have this here that I can write this. 1 second. We can do it, but we have to be a little bit careful. And the compiler would have to be very careful, but for these type of questions, you are the compiler. At least in terms of our dependencies here, in theory at least, there's no dependency between, I'm having trouble drawing this, there's no dependency, as always, between this instruction and this instruction. Brutal. But there's no dependency between that add IU instruction and that load word instruction. So in theory, we can move that up. There's a write after read dependency, and there's a read after read dependency. But for our MIPS pipeline, by moving that add IU up to become the second instruction, we're not violating any of those. So it's still okay by moving it up a little bit early. Other thoughts on making that move? And that would then, that's supposed to be an arrow I'm drawing. That would prevent the load use hazard because it'd be a load immediately followed by instruction that doesn't use the value being loaded, none of our logic triggers, and we're good to go. You're getting there. Yep, we have a dependency, right? By moving that add IU instruction up in order to fix the one dependency, we accidentally broke another dependency, right? One that we normally don't care about in terms of our pipeline's execution, but we care about because if we switch the order of it, we've broken our code, right? If we're not careful. This is a read of register S1 followed by a write of register S1. That is a write after read dependency. Again, from our pipeline's execution perspective for our nice MIPS 5-stage pipeline, we don't have to sweat it. We can circle them as a dependency. We don't have to worry about it from a performance perspective. Now that we have moved that instruction up, though, our code's wrong, right? We've broken that dependency, and the value that we're loading from this store word instruction, the address we're using to store into memory is wrong. It's off by 4, right? It's 4 fewer than it would be otherwise because we moved that -4 operation earlier on. The nice thing, and again, this is a textbook example, that's why everything works out so perfectly for us here, um, is because it's a store word instruction. And for any I type instruction with this type of relationship, we'd be able to do something similar. Ah, I give up. Because there is an immediate type that we're directly encoding there. There we go. We can just update that encoding. We've subtracted 4 a little bit early. We eventually do want to subtract 4, so we're not wrong from that perspective. So we'd want to replace that value with a 4. Let's all make fun of Joe who can't use his own technology here. 4. There we go. And now our code is correct. And not only correct, I mean, that's important that it's correct, of course, that it's not um, calculating the wrong value. It's also performing better. Again, it's a synthetic example. Now, what this question doesn't say, and to be a complete question, it would have to say what is potentially going on. It would have to say something about what's happening with our branch delay slot or not. Doesn't say. So I would argue that's it. We're done with this question. Full points. If I ask this on a quiz or an exam or whatnot, I'll be a bit more specific. If we assume we have a branch delay slot in which we as the compiler are attempting to fill our instruction after the branch instruction with something meaningful, that's the assumption we have to make for there to be any more point to this particular question. Then there's one more thing we can do. Because that's the only reason that no up would be there, right? That no up is there to show that, and again, the question doesn't say it, but that's why the no up is there, right? To show that the compiler tried to insert something valid after the branch instruction to always be executed, but it couldn't, or it didn't try very hard, so there's a no op there. So from a performance perspective, as we're adding up the cycles associated with this code, again, I always want to couch this appropriately. The question would have to be more precise with regards to what it's asking, but this is the hypothetical we're going with here. Originally, before we reordered the code, the assumption we would start with would be how many cycles it takes to get through this code, each loop. It would be 1 for load, 2, 3 for add u because of that stall that was there, 4, 5, 6, and then 7 for that branch not equal. And that's what the textbook is getting at with this example. That we count that no op because that branch delay slot only makes sense if we actually do in fact fetch, load, execute that subsequent instruction after the branch. So given that hypothetical or given that more precisely stated set of assumptions, what else can we potentially do to this code and we've cut off one cycle, so that's great. Can we cut the other one? How would we do it? So if we move the okay, so that's a good point. So we already moved the add IU. I couldn't see it on my screen here. This one's already over here. We've already updated the store word instruction. So in our updated version of the code, it's store word followed by branch not equal. If we look at those, there is a read after read dependency, right? It looks like we're writing, but we're not. That's a branch. So it's reading that register S1. So carefully, 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 what we could do, all right, what we could do, in theory, is move that store word instruction after the branch in lieu of the no op. That is again assuming there is a branch delay slot that every instruction after the branch, the single instruction immediately after the branch is guaranteed to be executed. If we assume that, then we might as well put the store word after the branch. Logically, we always want to store word first and then do the branch. Logically, that makes a lot of sense, right? We're doing the stuff in the loop and then we're going back to the beginning of the loop. But with that, if we assume there is a branch delay slot, that's still our basic logic model for what's happening in terms of our code's execution. With that little wrinkle of that, well, you can actually think of a branch as a branch and do that next instruction is how you'd want to think about it. And consequently, if we can put something meaningful there that isn't just a no op, which is what we're doing here, then we've saved on that one cycle of execution as well. We've gone from 7 cycles for this code base back down to 5 per loop. And if we look at it, it's 5 instructions. So 5 cycles is as good as we can do for our textbook scalar pipeline processor. Let's leave things here for today. If there's another late night tonight, for Project Part B, I understand that. I don't want to give maybe unfair advantage to some folks versus others in terms of additional help at this very late hour. But I'll be up as well. So finish up what you can, submit what you have by your deadline today, and let's all move on to Project Part C. And again, you should be very proud of what you've been able to accomplish. Of course, even if it's not perfect, it's never perfect. The companies that make billions and billions of dollars to produce these chips do not do it perfectly, and you shouldn't expect you should be able to do it perfectly either. But you should be proud of what you've accomplished and proud of what you're going to finish up in these last couple of weeks here in the semester. So do your best, and look forward to seeing everyone on Friday.